So let's take a look at worksheet 6, that first series of problems there. We have a system with 3 reactants, 2 products. Before I even get into the data, I'm going to say, well, these are the things that can affect my rate of reaction. My general expression for this problem is that rate is equal to some constant K times A to some order times the concentration of B to some order times the concentration of C to some order. That's the first thing I want to do. I've got 3 reactants. I've got 3 factors to consider. So through the wonders of pausing, here's your data. Lovely. So I want to consider A, B, and C independently. In a well-designed series of experiments, you change one factor at a time. At least they told me what I'm measuring this time. I'm measuring the formation of D. All right, so this is what I'm measuring. It looks like between experiments 1 and 2, the only thing that changed was B. It looks like they cut B in half. Now, from experience, I can tell you, you want to work up, not down. When I say up, work from lower concentration to higher concentration. So don't think of it as B being cut in half between 1 to 2. Work 2 to 1. Say this way, I doubled my concentration of B. What happened to my rate? Nothing. Doing a change in B had no effect. That's a zero order situation. Now, if B is zero order, and there's a 0 in there, anything to the 0 power is 1. B has no effect on my data, on my rate of reaction. I don't need to consider B at all. I'm going to cross out that entire column, and that's going to simplify my data table considerably. So we've established that B has no effect. Okay. Now I look for a series of experiments where I changed only A or only C. If I look at experiments 2 and 3, C did not change, but A did. I doubled A. What happened to my rate? It went times 4. So if A goes times 2, my rate of formation of D goes times 4. I believe that's second order with respect to A. I'm going to put a 2 up in here. So now I've determined B has no effect, A is second order. Now I want to find a series of experiments where the only thing I change is the concentration of C. Well, certainly down here, C is lower. C stayed constant, but then it was lowered. Okay. Well, look here. In experiments 2 and 4, A doesn't change, but C does. Working up once again, going this way, I doubled C. And my rate doubled as well. Oh, that's first order. It matched it. If it's first order, I put a 1 here. So now I can simplify my rate expression and say, all right, the rate law expression for this system, rate is equal to some lowercase k times the concentration of A squared, B has no effect, times the concentration of C to the first power. Question number 2 asks me, in experiment number 2, what about the rate of formation of E? In experiment number 2, I know that D was forming at a rate of 2.0. My stoich between E and D is 2 to 1. So in experiment 2, I've got D at a rate of 2.0. And my stoichiometry tells me I form 2 E's for every 1 D, which would mean E is going to be forming at a rate of 4.0. Question 3 says, in experiment 3, what about the disappearance of B? Yes, reactants are going to disappear. I know in experiment 3, I've got D appearing at 8.0. But they're not asking me about D. They've asked me, what about B? And my stoich says, well, it's 2 B's for every 1 D. Looks like 16 B to me. Interestingly enough, they didn't ask me to solve for K in this set, but I think we should anyway. You've got some space at the bottom of that page. What's the value of K? Well, how do we go about doing that? You have 4 experiments from which to choose. So you say, all right, my rate law written in red here, rate is K, A squared, C. I'm going to pick experiment 1 just because. My rate, 2, is equal to K times A, 2.0, squared, times C, 2.0. Oh, okay, so 2 is equal to K times 2 times 2 times 2. So I'm going to divide out here by 2 and by 2 squared. And that solves it for K. 2 divided by 2 divided by 2 divided by 2, I get 0.25. Alright, so much for the quote-unquote well-designed experiments. Next video for the ones where something went awry.